I'm going to tell you a little bit about reflectivity. Assuming I can change. There we go. Okay, let's go back. So if you're thinking about doing an X-ray reflectivity measurement, you typically have in mind something like this cartoon that I'm showing you on the left here, this cartoon here, which shows you the interface, in this case, between two liquids, water and dodecane, or you might be interested in studying the water surface, that is the interface between water and vapor. And you typically will think of having some kind of assembly of molecules at that interface. In this case, I just happen to have drawn something that is fairly well ordered. And what X-ray reflectivity allows you to investigate is the variation in the electron density profile. That is, how does electron density vary as you go, let's say, from the water interface along the perpendicular to the interface, sometimes called the normal, through the layer and into the other interface or vapor. And on the left here, I've plotted this depth parameter versus the electron density profile, where the electron density profile has the units of electrons per volume. So it's a local electron density that varies with this coordinate z. And here you can see this dashed line seems to bear some resemblance to what I drew on the right, but not that much resemblance, right? The dashed line doesn't have any indication that there are atoms there. It's showing you something about the average profile, and we'll be talking more about what is meant by average here. But for now, this value down here is some sort of average value in the bulk water. This higher value of electron density over here represents the fact that in the head group region, there are more electrons per unit volume. As you go here, there's a flat region which represents some kind of average electron density within this tail group region. At the end of the tail group at the top, it turns out the electron density drops a bit, and then you go into a flat electron density representative of the average electron density in the organic phase. This is what we call the intrinsic profile. However, what you measure in X-ray reflectivity is a bit different from this, because in a real system, there will be thermal motion of all of these molecules, the solvents, the molecules at the interface, and the net effect is to sort of smear out this intrinsic profile to give you what I've shown here in red, which is sometimes called the effective profile, but that is what X-ray reflectivity actually probes. So before we get started, I want to just talk a moment about the goals of these lectures. There'll be 3 of them, as Wei mentioned. I want to introduce you to some of the basic theory of reflection, and then show you some simple to use calculational tools. So some of these tools will be the kind of things you can do with pencil and paper, but others will be actually rather sophisticated computational numerical tools for analyzing data. But in both cases, we're hoping that they're simple to use. And then finally, I will be spending a fair amount of time trying to provide you with some intuition about why a reflectivity curve, such as this red one on the left here, represents what's going on the right here. Well, actually, this is not the reflectivity curve. This is the electron density profile, but intuition about what the reflectivity curve will look like. Of course, there are many other things that I won't be able to talk about, many advanced topics, some might argue some basic topics as well. And there are places in the literature you can look for this. A few years ago, Peter Pershan and I wrote a book on this, whose cover page I'm showing you here. So that's another place to look for a lot of this material that I will cover and won't cover. So let's start out with the reflection geometry. Here we imagine, here's our interface. We shine X-rays on that interface. We call those the incident X-rays. They come at an angle alpha with respect to the surface. So typically when you talk about optical reflectivity in the visible light range, you talk about an angle with respect to the normal. Here, when we talk about X-rays, we talk about angles with respect to the plane of the surface. The reflected beam comes off here. In the situation that we're describing, which is sometimes referred to as specular reflection, So people say specular reflection when they want to make sure you know that we're considering a situation where the reflected beam comes out at the same angle. I labeled it also alpha sub I as the incident beam comes in. Often people just say reflectivity and don't specifically mention specular, but sometimes people refer to reflection in a much more broad sense. So you need to say specular sometimes. And then there's a transmitted beam, a beam which will go through the interface into the lower phase, and that comes off at its own incident angle. These three lines here represent the typical range of angles that one would use to measure X-ray reflection from the surface of water. Just wanted to show them to you so you get an idea what they look like. This line here is about 4 degrees from the other two lines, and yes, there are two lines there. They're separated by on the order of 1/10 of a degree or less, and it's often true that X-ray reflection or other X-ray scattering studies from liquid surfaces are carried out at very small incident angles. Now let's think a little bit about the electric fields. Of course, X-rays are electrodynamic waves, just as visible light is. And so each one of these lines represents a traveling electric field. And so let's just characterize them. Typically, if you're working at a synchrotron, the synchrotron beam is polarized, and it's usually polarized so that the electric field is coming out of the monitor, either towards or away from you. So I've indicated by that by writing each of these electric fields, the incident, the reflected, and the transmitted is in the x-hat direction. So the x-hat direction is out of the screen, either towards or away from you. Then each one of those fields has an amplitude, EI, ER, and ET. And in addition, it has this exponential piece, which is the piece that expresses the oscillations in both space, that's the k dot r piece, and in time, minus omega t. So these are traveling fields that oscillate in space and time. Now this, I think, will be the last time you see this minus omega t in these lectures. That appears the same way pretty much for everything that I'll be showing you, so it generally cancels out. And our focus will be on this k here. For example, this k vector, the wave vector, in this case, the incident wave vector, points in a particular direction. In this case, it's pointing in the direction of the incident X-rays. It points in different directions for the reflected, transmitted. But interestingly, almost our entire theory discussion here will be centered on these k vectors. So first of all, let's remind ourselves what a wave vector is. If we took the magnitude of a wave vector in a material and we divided by what I call k naught. K naught is just the magnitude of the wave vector in vacuum, which is simply related to the wavelength. Before I go on, let me just remind you that these wavelengths are quite small, typically on the order of an angstrom, less than half an angstrom, typically for 30 keV energy X-rays that are used to study liquid-liquid interfaces, typically slightly more than an angstrom for 10 keV X-rays that are used to study liquid vapor interfaces. But let's go back to the magnitude of the wave vector. You take the magnitude of the wave vector and divide it by this vacuum value, you get what's known as the index of refraction. This is the same definition that's used for optical waves. The rest of it is a little bit different because X-rays interact in a rather specific way with material. So let's just think a little bit more about what this expression means. I've just repeated that expression up here. You can see that the index refraction has a real part, is 1 minus zeta, and the zeta has this somewhat complicated expression, but I just want to point out to you this piece here. The zeta is proportional to rho. That's the electron density rho that we've been talking about, the number of electrons per volume. There are some other things going on in this expression for zeta. I'll discuss those in a minute. But let's go back to the index of refraction. That also has an imaginary piece, I beta. And if you remember from your study of optics, the imaginary part of the index refraction is responsible for absorption. So in this case, as an X-ray passes through a material, it's absorbed. And it's absorbed according to this value beta, which is also proportional to the electron density rho. So we see that the index refraction here, the n, as well as the magnitude of the wave vector k, depends critically on this electron density rho. And that's because X-rays scatter from electrons. That's the basic physical process that makes X-rays scatter. And that's what produces the reflection and all of the other effects that we will be talking about in the next day or two. So let's look at some of these other little pieces here, which I've given you to some extent for reference. R sub E here, which appears in both zeta and beta, is what's called the classical electron radius. If we had an electron that was sitting in free space and we would shine X-rays on it, there would be a certain amount of scattering of those X-rays. And the amplitude of that scattering is directly proportional to the classical electron radius, R sub B. But generally, electrons are bound inside atoms. And so we need a correction because the scattering from those electrons is changed because they're bound inside atoms. And those corrections are labeled F prime and F double prime. Sometimes they're referred to as the anomalous dispersion corrections to the atomic scattering factor. And also you see a Z in here in these expressions, and that Z is just measuring the atomic number or the number of electrons. Now, it's interesting to realize that zeta and beta in this index refraction N are both very small. Zeta is on the order of 2 parts in a million. Beta is on the order of 1 part in 100 million. And that's, for the typical energies that are used at chemat cars and for common aqueous and organic solutions. So what we see here is that the index of refraction is less than 1. So that's very different from the optical regime where the index of refraction is always greater than 1. But it's only slightly less than 1. So if you go back up to this equation, you see in terms of its real part, it's only 2 parts in a million less than 1, nearly equal to 1. This has a very important effect on reflection of X-rays from materials. It makes the angles for total reflection, which I'll discuss in a little while, very small. And it also confines measurable reflection to very small angles. Now, before we pass to the next part of this, let's talk a little bit about absorption. So this imaginary part I beta is providing you with the absorption. Absorption, of course, refers to the fact that when you have some sort of X-ray wave passing a distance r through a material, the intensity varies exponentially. It's reduced because the material absorbs some of the X-rays. It's reduced by minus the distance it travels divided by this absorption length. And the absorption length is determined entirely by beta, this imaginary part of the wave vector, plus of course the wavelength, which is in the K naught. Sometimes this length, L absorption, is written as an inverse length, and that's called the linear absorption coefficient, U sub L. Now that we understand how to think about the index of refraction or the wave vectors, let's think about how we determine reflection and transmission at an interface. And it turns out the way you do this for X-rays is exactly the same as the way you do it for optical visible light. And so if you want more details of what I'm going to talk about, you can consult your favorite electrodynamics book, assuming you have one. If you don't, this is a reasonable book to consult. So one of the key things here is that the only thing that's changing in our sample, or the only thing that's changing that we're modeling really, is the electron density variation with Z, or equivalently, the index refraction variation with Z. And so under that condition, the general laws of reflection and refraction, as you could look up in these books, tell you that the in-plane components, that is within the plane of the surface, that the X, the Y is in this direction, X is coming out, the X and Y components of the wave vectors are equal. That is, the X components of the incident, reflected, and transmitted wave are all equal, and the Y components of those 3 wave vectors are all equal as well. That leaves us with just the Z components. That's the only thing we have to work with in determining reflection and transmission. And as you'll see, they determine what the critical, the reflection and transmission coefficients, which tell us what we want to know. So let's think a little bit about how we would do that in a simple case. The general result is, let's say you're far from the interface. Let's say we're right here, this region of Z here. In this case, there are, at this Z value, right, that Z value extends over here, also includes this wave. But here, we have a wave coming in. I'll represent that this way. I've removed the minus I omega t, as I claimed I would earlier on. And I'm also going to just set the amplitude of this incident wave to be 1. So that's not there explicitly. Here, so this is representing the Z variation of the wave that's coming in, the incident wave. And then for the reflected wave, I have a similar Z variation, except in the incident wave, there was a minus sign here that indicates that the wave is going down in the negative Z direction. That minus sign is missing here because the reflected wave is going up in the positive Z direction. But we also have this coefficient that just says that the whatever's in the reflected wave has a different amplitude than the incident wave. And that's referred to as the reflection coefficient R that I mentioned a moment ago. Similar sort of result occurs for the transmitted wave. That is, if you're down here, there's a wave passing through. It's going in the negative Z direction. So you have the e to the minus I kzz. And then we have an amplitude again, because the intensity of, or the amplitude of the electric field in the transmitted direction is different from the incident, which was 1. And that amplitude there is called the transmission coefficient. So what we want to do is you want to solve for these transmission and reflection coefficients. And we can do that, as I mentioned in the previous slide, just by using boundary conditions. I'll show you this for a very simple situation, what's referred to as a step function interface. That is, the electron density varies like a step. That's what I'm showing you here. At negative Z, when you're in the lower phase, I'll call the electron density rho sub t, meaning that this is the electron density in the medium which has the transmitted wave. And in the upper half space, I'll call the electron density there rho sub I, again, the electron density in the medium where the incident wave is. And there's just a sharp step function variation between these two. The boundary conditions here are simple. As you imagine going through the interface, the electric field remains continuous as you cross the boundary. It's equal to 0. And the derivative of the electric field with Z, the derivative in this direction, remains continuous. So if you use these conditions, let's imagine, how would I use these conditions? Let's say I wanted to calculate the continuous E of Z at Z equal to 0, then I would go back up to these equations. And I would just put Z equal to 0 in here. When I put Z equal to 0 into this first term, I would just get 1, right? E to the 0 is just 1. Then I would get 1 plus R. Here I would get a T because all these exponentials become 1. And I would set these two things equal to one another. This is the field right above, and this is the field right below, but it's equal to 0. And so that would give me an expression 1 plus R is equal to T. And if you can do the same kind of thing with the derivative, take the derivatives of these, then you substitute Z equal to 0, you set these two equations equal to one another. So then you have two equations and you have two unknowns, and that just allows you to solve for the reflection coefficient R and T, and that's what we've done down at the bottom here. The reflection coefficient is defined as the ratio of the electric field of the reflected wave divided by the electric field of the incident wave. And so in the transmission, in a similar way, the electric field of the transmitted wave divided by electric field of the incident wave, and you get these simple expressions just by applying these two boundary conditions. And you can see, as we expect, because nothing else is around in our equations, that these reflection transmission coefficients are entirely described by Z components of the incident and, in this case, transmitted wave vectors. Then we get to what's called the reflectivity. The definition of the reflectivity, R, is capital R, not little r, but uppercase R of alpha, is the ratio of the intensity of the reflected wave to the intensity of the incident wave. So let me just remind you what intensity is. Intensity is the average power per unit area, or the average energy per time per unit area. We're averaging because these waves are fluctuating wildly, very rapidly in time, so we just average over that time. So you can see by the fact that this is an energy per area per time, that what the reflectivity gives you is a fraction of the incident energy that's reflected. So a certain amount of energy is incident in the incident X-ray beam onto your surface. Some fraction of that is reflected. And that is what we call the reflectivity. And of course, the intensity is related to the square of the electric field. There are a few other parameters in front, but in the case of this calculation, all those parameters cancel out. So in this case, the intensity is just the division of the electric field squared of the reflected and incident waves. And that, of course, is the way we define the reflection coefficient. We showed that just a moment ago. And that's given by this expression, which is just what we had on the previous slide, except we took the magnitude of it and squared it. This is called the Fresnel reflectivity, not just any old reflectivity, because it's the reflectivity that corresponds to a step function change in the electron density profile. If we had some other kind of change in the electron density profile, let's say it varied smoothly, then we would no longer call it the Fresnel reflectivity, but we'd have some other expression for the reflectivity. Here I'm showing you what the Fresnel reflectivity looks like for a liquid gold vapor interface. Never let it be said that Chemat cars is cheap. So you can see that here I plot the reflectivity. It has a value near 1, then drops off rapidly. However, I plotted it not versus the incident angle alpha, which is what I had up here at the top, but I plotted it versus QZ. So QZ is what we normally use when we're thinking about the reflectivity plots, and it's called the wave vector transfer. And let me see if I can explain that name to you. So we start out with an incident wave vector going in this direction down here. And then we transfer some additional wave vector component to it. That's this QZ. And when we finished with the incident plus the transfer, we end up with the reflected wave vector. That's just this wave vector that I moved up here just for convenience. So the general definition is the wave vector transfer is the reflected wave vector minus the incident wave vector, or even more generally, if you're talking about some other scattering process, it's the scattered wave vector minus the incident wave vector. And in this particular case for specular reflection, where the incident angle and the reflected angle are the same, the wave vector transfer has only a z component, QZ, and it's given by twice the magnitude of the incident wave vector times the sine of that incident angle. For liquid vapor, you can write it, for liquid vapor interface, you can write it in terms of the K naught, that is the magnitude of the wave vector, or sometimes just called the wave number in vacuum, which is just 2 pi over lambda. So then you get this expression, the QZ is 4 pi over lambda times sine alpha, where alpha is the incident angle. Of course, the other thing to notice is that because the only component that survives is a z component, that qx and qy are 0 for specular reflection. Now let's think a little bit more about this liquid gold vapor interface curve. As I said, this reflectivity goes to 1 at small angles, or at small q. Remember, q is basically now just the sine of the incident angle. But it actually reaches 1, or very close to 1, slightly before you get to 0 QZ, at the point right around here, where QZ is equal to what's called the critical Q for total reflection, which we'll call Q sub C. Q sub C is, of course, just going to be very close to 4 pi over lambda sine of alpha C. I'll show you where this expression comes from on the next slide, but for now, let's just use it. You can see that it goes like the square root of delta rho, where delta rho is the difference, that is, it's the electron density in the lower bulk phase, that is the phase that has the transmitted wave, what I call rho sub t, minus the electron density in the upper phase, the phase that has the incident wave, rho sub I. Sine alpha, C is the critical angle, as I said. Now I'm going to neglect f prime, which is often appropriate, not always, but often. And we get this rather simple expression for the critical Q. It just has these constants times the square root of this delta rho. In the case of a liquid vapor interface, of course, delta rho is just the electron density of the lower phase, because the electron density of the vapor is basically 0. And you could calculate the critical Q for a water vapor interface. And so this, for many of you who are interested in doing experiments on water surfaces, this is a useful number to know. It's about 0.02 inverse angstroms. Of course, this critical Q goes as the electron density. So for something like liquid gold, which has a much higher electron density than water, you expect QC to be higher. And it turns out that this critical Q up here is something like 0.07. Now, the other thing we notice is that there's a very rapid decrease of the Fresnel reflectivity with QZ. Now, in these lectures, I'm occasionally going to have some math that I'm not going to go through generally, but I've included it in the lectures just for those of you who want to kind of work through these things. This will give you some hints about how to get there. It doesn't show you all the details. But anyway, what I want to do now is I want to show you a simple approximation for the Fresnel reflectivity. And you can get that by rewriting things more or less the way I've described here. But let's just go to the result. And the result here is very interesting. It shows that the Fresnel reflectivity, to some approximation, can be thought about as this ratio of QC over QZ. So of course, it's changing with QZ, and that's sort of been normalized by QC. So you can think of for Fresnel reflectivity as QZ, excuse me, being given in units of the critical QC. But also we see that the Fresnel reflectivity goes as 1 over QZ to the 4th power. And that's what's responsible for this rapid fall off in intensity here. That's just going like 1 over QZ to the 4th. Now this approximation is shown by this dashed line here. And you can see the dashed line is not exactly meeting the exact calculation for some range, but after that, it's quite accurate. So the approximations that I made in this math lead to this simple approximation only being accurate when QZ is on the order of 4 QC or greater. Now let's think a little more about what's going on below the critical angle. And to do that, we have to think a little more carefully about the Z dependence of the transmitted wave E of Z below the critical angle. To do that, of course, we can go back to our previous expression, and we see that what we need to do is we need to evaluate the Z component of the transmitted wave vector a little more carefully, particularly for very small incident angle near the critical angle. And again, here's a mathematical aside. I'm not going to go through this. I'll just point out that there is one approximation here, but this is approximation that's generally valid, and that is we need small zeta and zeta being much greater than beta. And as I said before, for the kind of materials that we're typically interested in here, zeta is about 2 parts in a million, and beta is about 1 part in 100 million. So this is a good approximation. And that leads you to this expression for the Z component of the transmitted wave vector. Just so you see, it has a square root. And of course, this square root will be fine. We'll get a real number for that Z component when the incident angle squared is greater than 2 zeta. But when the incident angle squared is less than 2 zeta, then this component becomes imaginary. At that point, that's when the total reflection occurs. And so we say that alpha C is approximately the square root of 2 zeta. So we can see that that corresponds to total reflection by looking at, excuse me, looking at, sorry about that. Looking at this exponential, we can see that here, if k, let's go down here, if k is real, that leads us to a traveling wave because we have this minus I. But if k is imaginary, then we get exponential decay. We get e to the ktz. The double prime here indicates that's the imaginary part times z. Now you might say, well, this doesn't look like exponential decay, right? It's got a plus sign, but you have to remember that in the lower phase, z here is negative, so that the integrand for this exponential, the argument for this exponential is negative. And that leads us to an exponential decay, which I've indicated by this green line here. Now, one other thing, excuse me, is going on below the critical angle for total reflection, and that is, here I show you the detail for our liquid gold vapor interface. Below the total reflection, you would expect that R is 1, but it isn't actually 1 because, excuse me, sorry about that, because there's an evanescent wave, this exponentially decaying wave in the lower material, and there's some absorption. So the reflectivity is a little less than 1. Now, before we leave the critical angle, let's ask what are the length scales here? Over what length scale does this exponential decay happen? And so we can, again, go back to this transmitted expression for the electric field. Instead of writing this as plus k double prime times z, I'm going to define this decay length, lambda. So now we have this exponential decay z over lambda. Remember, z is negative here. And so we can write this inverse decay length, lambda to the minus 1, in terms of this difference in angles, k naught times the square root of alpha c squared minus alpha I squared. If you look at values when alpha I is much less than alpha c, so then it's basically k naught times square root of alpha c squared, or turns out that's just a convenient way of writing the critical q value. So lambda goes like 1 over qc. Then you get these numbers that the decay length for, actually, let me take a step back because I don't want the decay length for the field. I want the decay length for the field intensity, which is half of that of lambda. So the decay length for the field intensity is about 5 to 10 nanometers when you're far below the critical angle for water and common organic liquids. This is very useful because this evanescent wave now is confined to within 5 to 10 nanometers of the interface and can be used for grazing incidence diffraction and fluorescence. And that'll be discussed more later in this school.